Okay, so I will hop on here and wait for you guys to hop on. I'm pulling up my chat right now, so you'll be able to talk to me there. So if I don't see you just yet chatting to me, give me a second while I pull up my Restream chat. And I use Restream to help me broadcast on both Periscope and YouTube. So I see we got 3 people on here. All right. Hi, hello. Hello everyone. How are you guys doing? I hope you're doing well. Because today we are going to talk about the awesomeness that is the Big Bang Theory. It's snowing there. Oh goodness. It's not snowing here, but it is very, very cold. The TV show. Not the TV show. We're not talking about the Big Bang Theory TV show. We're talking about the actual Big Bang. So I hope that's okay. You guys are doing fine. Fantastic. Do you have a presentation or will it be Q&A? I always have a presentation, but the wonderful thing about my show is that you can ask questions while we're going through it. And if I don't have the answers right away, fear not. I will find the answers for you and direct you to those sources at the end, possibly on Twitter. But I always put all of my sources in association with my presentations on my website, scientistmel.com, to where you too can go and possibly have your answers answered for you in regards to the sources that I use. So I will actually be doing that. What's in the center of the Big Bang massive black hole? No, probably not. So since you guys have hopped on, let's go ahead and get started with the show. You guys ready? So that's one of my intros that I have. I have several different intros that I get to use because Gonna Go For It has made them for me and he's very kind to do so. So that's one of my alternate intros. I like it. It's pretty cool. So let's go ahead and hop on to what is this groovy thing called the Big Bang Theory. So what I'm going to talk about essentially is what is it, the time frame, and what's the evidence associated with the Big Bang Theory. Here in New Jersey is where the background radiation was discovered, I think. Possibly. Hello everyone who's hopped on. So essentially what we're looking at is the universe is approximately 13.8 billion years old. That's pretty old. And so when we encounter individuals who are like, universe is only 6,000 years old. Well, science tells us that that is not the case in regards to how old we have things in our celestial bodies in our universe that we're able to measure. And I'm going to talk a little bit about how it is that we have this particular information. So the first thing we have to do is talk a little bit about how the age of the universe has come to be. All right, so how do scientists determine the age of the universe? Well, they do that by studying the oldest objects in the universe and also measure how fast it's expanding. So the universe, essentially, I think everybody can agree that the universe cannot be younger than the things in it, right? The universe cannot be any younger than the things that are in it. So determining the ages of the oldest stars gives us the ability to put a limit on that age. So we can put a limit, say, okay, well, it can't be any younger than the oldest star, right? The life cycle of a star is based on its mass. Now, mass is something that we can measure. Now, in regards to stars, the bigger the stars, the faster they burn. The brightness of the stars are also associated with the mass. The brighter they are, the bigger they are. Now, the thing that can be a little bit hairy in regards to this is that distances between stars and us can make pinpointing that exact mass difficult due to the brightness. So scientists could get a little bit off in regards to how old a particular star is, because the distance can play a role in how bright that particular star is, and brightness is linked to mass. Now, globular clusters. These are essentially groups of various stars. Now, they behave similarly to stars alone. So those are studied as well to help determine the age of the universe. Now, this uncertainty that scientists have leads scientists to believe that the universe cannot be younger than 11 billion years. So they understand it cannot be younger than 11 billion years because of the fact that of what we have. So when you take into account that uncertainty, 11 billion years, it can't be younger than that. However, it can be older. Have you had to deal with students that were taught about a young Earth by family? Well, in the past, when I was a high school teacher, I did have students who did not believe that, for instance, the Earth was older than 6,000 years. They had a hard time wrapping their head around that idea. But once I presented the evidence and I made it plain that I wasn't there to try to change their mind, I wanted to make certain that they understood what the evidence was, and then they could make up their own minds. They were still welcome to believe whatever they wanted, but they needed to understand what the evidence was. And I find that when I allow them a space to be able to contradict in their own minds, if they chose to, allow them a space for that and say, yeah, I'm not here to change your mind. I just want to make sure you know what the evidence is. And that you thoroughly understand what it is that scientists are studying. And then you make up your own mind. It's not my job to do that. So that way, hey. All right, so how? Somebody said billions of stars, including the one that's unobservable. How do you know which is the biggest and oldest? That's a good question. But the ones that we know, that we're able to see and can definitively determine the mass of, allow us, when we take into consideration that uncertainty that you mentioned there in that question, the ones that we're able to observe and see cannot be younger than 11 billion years old. So it's possible that they could be older. So now that we've talked about the mass of stars, so the bigger the star, the faster it burns. The smaller the star, the longer it burns, and the brightness has to do with that. So when we take into consideration the observable stars that we have, and we know for certainty that these particular stars cannot be younger than 11 billion years old, that's where we get that calculation. All right, the expansion of the universe and its rate are also key in determining the age of the universe. All right, so one number that you may not be familiar with is Hubble's constant. This is the rate of expansion. That's how fast the universe is expanding and growing. Now you might ask yourself, how is this number determined? So by studying the types of matter in the universe that we have, the proportion of dark matter to dark energy, as well as the density of matter, a universe with a low density of matter compared to matter-filled universe is older. So how do you think about that? All right. So a younger universe is going to have more pieces in it. It's going to have more bits of matter. An older universe is going to have less amount of matter. Because essentially, when we take into consideration chaos, the universe is going to bits. So we would expect to see less bits of matter, less big old chunks of matter. So Again, a universe with a low density of matter, that means it's all compacted together. So we have less dense matter compared to a matter-filled universe, is going to be older. So remember chaos, the universe is going to bits. Hello everyone. So the other thing to think about in regards to this, the density evidence. Hello. The density evidence. What in the world is going on with the density evidence? People would be freaking out. How do they get this density stuff? What is it? Well, we have wonderful organizations called NASA and the European Space Agency, which have helped us understand a bit of that. Can we observe the center of the universe by tracking the direction of the universe's expanding? That's a good question. And I'm going to touch on the fact that that's a common misconception, is that there's some kind of center of the universe, because there isn't. And I'll explain why, because it's kind of hard to wrap your head around. But I will happily talk about it. All right, so we have these lovely organizations called NASA and the European Space Agency, which allows us, through their missions, to be able to help us determine this density evidence. And they're also able to give us evidence in regards to background radiation. So some of you may not know much about that background radiation, so I'm going to give you a little bit of information in regards to what that is. So these particular missions that we have, all right, NASA's Wilkinson Microwave Anisotropy Probe, also known as WMAP, so I'm going to call it WMAP, that's that NASA mission where they're looking at microwave radiation, and the European Space Agency's Planck spacecraft. You might be familiar with the term Planck from the fact that Planck was a chemist, and so we have, and also a physical chemist. He was involved in thermodynamics. And so the European Space Agency had a Planck spacecraft. It measured thermal radiation left over from the Big Bang. Planck equals smallest. This helps determine the density, composition, and expansion rate of the universe. So this leftover radiation is what we call cosmic microwave background. Okay, now I'm going to talk about what that is a little bit later. So both WMAP and Planck spacecraft measured it. So they were able to measure this microwave radiation. Now the WMAP estimated the age of the universe to be 13.772 billion years based on this radiation. I'm going to talk about why the radiation is important in a little bit. So, and they had an uncertainty of about 59 million years. But, you know, and honestly, if we're talking about 13.772 billion years, millions of years seems a little bit mild in regards to fractions. And that estimation, you know, whether it's 11 billion or 13 billion, it's kind of like, you know, it's not incredibly substantial when we're talking about 59 million years, when we were originally talking about an uncertainty of about 11 billion. So CMB required by Frank Hoyle. All right, so this estimation of WMAP is fairly new. It occurred in 2012. Now the following year, you remember I talked about that Planck spacecraft. Planck estimated the age at 13.82 billion years. So those particular missions came back with really, really solid estimates. And these estimates fall within that lower limit of 11 billion years. So the thing is we have this measurement of this cosmic radiation that's coming off that in this density that we're able to measure in regards to the missions of the both WMAP and the Planck spacecraft from the European Space Agency and WMAP from NASA, two completely different organizations, come up with the 13.8 and 13.7 billion year age of the universe. So both have exceedingly smaller uncertainties than the initial number of scientists going, well, the oldest thing we can observe is 11 billion years old, but it could be older. And so this estimation is by far, in regards to these missions, much more substantial and considerably lower than the uncertainty by just what scientists have observed while being on our planet. Now, hello from British occupied Belfast. Oh goodness, you guys are funny. All right, so the other thing, okay, so NASA has a telescope called the Spitzer Space Telescope. It's also made strides in pinpointing the age of the universe by reducing this uncertainty of the Hubble constant. Remember, I mentioned the Hubble constant before. Why did you have to befriend a science denier? They're so hard. Odds are forever in our favor, yes. Oh goodness. So the Hubble constant, as I mentioned before, is the rate at which the universe is expanding. And so evidence from NASA's Spitzer Space Telescope has made strides in reducing that uncertainty in regards to the Hubble constant. So using all of these measurements combined, scientists were able to make independent calculations from not only NASA, but the European Space Agency, in order to understand and make these calculations in regards to the pool of dark energy, thus giving us a better understanding of the rate of expansion of the universe. See, when it was initially thought that gravity, since gravity pulls things together, that the galaxies would be coming closer together and colliding. But now we understand that they're actually being pulled apart, and that dark matter has something to do with that. And so we know that the universe is expanding. We know that galaxies are moving far apart, and we know that something is overcoming this intercelestial body gravity. That's where dark matter plays a role. Is the expansion rate of the universe steady? It's an acceleration. It's speeding up. We know that. So I don't have the actual rate right now in front of me. I guess I should have put that on one of my slides. But cosmological constant or dark energy. Now, in regards to, are you talking, what do you mean by a cosmological constant, Dennis? Dennis is asking me that. We do see, as far as I can understand, there is a steady acceleration. So it's moving at an accelerating type of rate. And acceleration is different than speed. Speed would be like when you're holding a consistent speed. Einstein's fudge. Yes, it's okay. So yeah, dark energy. Now that we know that dark matter and dark energy are involved in the universe, and we know it's there, there's something that's pulling galaxies apart. Dark energy and dark matter are still conundrums a bit to physicists and people in NASA because of the fact our planet's being pulled apart in any sense because of this pull. See, that's the thing. There's something that's pulling stuff apart, because you would think that our Earth has gravity, other planets have gravity. We should be moving closer together, but we're spreading apart, and the universe is expanding, and things are moving away from each other. So something's got to be pulling it apart to a degree. So that's where the dark energy and dark matter come into play. What happens after it expands to its max? That's the thing I'm going to talk about here in just a minute. There is no max. There's no lines that we know of. The universe expanding is not like you're filling air in a balloon. It's different. If expanding is speeding up, what does the Hubble constant stand for? I imagine that's probably at the time that it came out. And again, I'm speculating because I don't have the number in front of me. But the Hubble constant is the rate at which the universe is expanding. But they're able to refine it a bit more because they understand that it's accelerating too, and it's getting faster and having more information in regards to the microwave radiation and the density of seeing things that are less dense now. Things aren't as dense as they were, and they're moving apart. Density means it's coming together. You know, Gravity rules inside galactic clusters. Do you think it could get sucked back in? I think you mean creating a later new Big Bang. See, that's interesting, and I'm about to talk about that in just a minute. Creating a Big Bang. So, what I want to talk about now is the expanding universe, which I've got this next because we're talking about it more. What's that about? The expanding universe. What's that about? What's going on with that? So, since we're all on that, I want to talk a little bit about where it came from. I actually have a video on dark energy. Is it dark energy? I believe I have a short video on dark energy on my YouTube channel. It's about 8 minutes long. I am going to do another one on dark matter, so it'll kind of go well with that. So if you want to, you can always go to my youtube.com/c/scientistmel, or just search me on YouTube as Scientist Mel, and you can find my dark energy video. It's really short. Dark energy and dark matter are pretty freaking weird, and they behave strangely. And there's a lot scientists don't know about it, but we know it exists because you can see that it's pulling things apart. So, let's talk about the person who first came up with this idea that the universe is expanding and stretching and moving outward. And I probably will say his name wrong because I'm terrible at saying pronunciations of names that are of different countries. I'm terrible at it, so I wish to apologize in advance if I butcher these words. All right, this is either Georges Lemaitre, and if I said that wrong, I do not speak French well, and I'm willing to concede that I don't speak French well. He was a Belgian Roman Catholic priest who was also a physicist and astronomer, and he is the first person to come up with this particular idea that the universe is expanding. And so this is pretty phenomenal, and this happened in 1927. So let's talk a little bit about, I'm going to just call him George. I'm going to call him George, this Belgian Roman Catholic priest / physicist / astronomer who is like, the universe is expanding. It's fantastic. And so people want to listen to him. He has a Harry Potter look. He does, doesn't he? He does look. He's Harry Potter and the expanding universe. Wouldn't that be fabulous? Harry Potter and the expanding universe. When mass attracts, does that only apply to very small amounts since the universe expands? Well, see, that's the thing. Scientists are now understanding that dark matter is the majority of the universe. So there's dark matter here. And the matter that we see, that we exist in, is a small percentage of what the universe is made of. So, and in that regard, because there's so much dark matter, they don't know if it's like a liquid or if it's a fabric or how actually it interacts with things, but they know it does have gravity, and it's substantial because it's moving stuff apart that are huge, right? But dark matter is just space with nothing in it, right? Well, see, that's not necessarily true. So there are so many questions to answer, and there are lots of different things that NASA is looking into in regards to trying to understand what dark matter is and what it does. But they know that it has mass, and they know that it's pulling on things. Matter is like light icing on cake of dark matter. Yeah, kind of. That's a good analogy. All right, so George, the Harry Potter look-alike, who first came up with this expanding universe, he had a paper that was a homogeneous universe of constant mass and growing radius accounting for the radial velocity of extragalactic nebulae. That was the name of his paper, and that's the translation for it. And it was published in 1927 in the little-known journal Annales de la Société Scientifique de Bruxelles, and I probably said that wrong. So essentially, it's a scientific society of Brussels. So that's that journal. In this paper, this is where he presented the idea of an expanding universe. It also led to that derivation of Hubble's law. You remember that Hubble constant I mentioned? That the outward speed of distant objects in the universe is proportional to the distance from us. And that provided the first observational estimation of the Hubble constant. All planets in the solar system can fit in space between Earth and Moon. Oh, goodness. I don't know about that. I don't think that's not really true, because we know Jupiter is massive. Jupiter could not fit in between the space of Earth and Moon if you're talking about just literally right there. Jupiter's huge by itself. So, which nation has the greatest per capita of scientists? Man, I don't know. All right, so in 1929, so in 27, George came out with this paper, you know, talking about the expansion of the universe. Then in 29, Edwin Hubble published his paper that the red shift in light, so light can shift. You have blue shift, which moves one way. Red shift means another way. So the red shift in light coming from distant galaxies is proportional to their distance. So this confirmed George's prediction of the universe constantly expanding. I can't wait until they detect it and study it. And how does something with such a large impact on our universe stay so hidden? That's true. But see, that's kind of what makes things wonderful in regards to science, is that there are so many questions we need answered. And so that's when scientists go digging, like, what's this answer? What are the possibilities? But the thing is, they always look to evidence. There's a reason for it. So they need to find those, what is causing this to happen, and what is this dark matter? All right, so when we're looking at the universe constantly expanding, do I play pinball machines? I do sometimes. Hubble spoke with affected English accent. All right, so if we look at the expansion and movement of matter, that had to come from somewhere. This movement is happening. If we even look at Newton's laws, you know, objects in motion stay in motion, but there's got to be something that's caused this initial motion. And that's where we get this initial event. Would not be surprised if actually the Vatican, with its few hundred inhabitants, would qualify as the nation of scientists. Oh, yes, that would be fantastic once we figure out what the dark matter is. So, we don't even know what's in the ocean. That's true. The ocean is the least explored biome on our planet, to be honest. You know, so let's look at this. The Big Bang. What the heck is it? What is it? After all, they also have a stellar observatory and other science-related committees in there. They do. The Vatican does participate in science. That's correct. So, what in the heck? Am I Bill Nye's girlfriend? No, I'm not Bill Nye's girlfriend. Why is he looking for a lady? Oh my goodness. A show on CBS. Oh my goodness. You guys are funny. Bill Nye's girlfriend. No, but Einstein's always backing me up, isn't he? Einstein's always in my background. He's a fun guy. So now I want to talk a little bit about what the Big Bang is, and essentially what it is that scientists understand to be the case. So I'm going to kind of break down the events for you. Yeah, Einstein's got my back. I want to kind of break down the events for you so you can kind of get an understanding of what the timeline is. All right. He's got your back, Einstein. I'm great to do this. So I'm glad that you guys are enjoying this. All right, so the Big Bang. It started out with tiny hot particles of light and energy. They expanded. We know things expand. We can see that. And then it cooled down. Once that cooled down, those particles then formed atoms. These atoms formed stars. These stars formed galaxies. Now, the first stars made even bigger atoms. And then these atoms made molecules. And then this led to more stars being formed. Now, while all of this is going on, In the bottom line there, while all this is going on, galaxies crashed and grouped together, new stars were born and others died, and then finally, after all of this stuff happened, we got asteroids, comets, and planets formed. So this is kind of like a breakdown of a timeline of what happened with the Big Bang. Where did the first particles come from, though? That's right. What is that called? The, oh, what is that called? The is it Bolin-Hughes? The Bolin-Hughes particle? See, I can't remember everything all the time. See? Bolin-Hughes, isn't that the particle, the initial particle? And that they were trying to recreate with the Hadron Collider? Higgs boson, Bolin-Hughes. Why am I thinking of Bolin-Hughes? I think that's a street near where I live. Lost me with the Bolin-Hughes particle. Higgs boson. You guys caught me. I think Bolin-Hughes is a street not far from my house. Oh, Higgs boson particle. That's the particle that they were trying to do with the Hadron Collider. Higgs boson particle. Yes. So if you're not familiar with the Higgs boson particle, you should check it out. It's pretty interesting stuff. And I can send you links to Higgs boson if you need. Bolin-Hughes. I think that is a street near my house. See, science communicators can mess up words sometimes, and it's entirely hilarious. So let's talk a bit about the Big Bang in regards to specific events. All right, but I want to talk about, yeah, some people call it the God particle. That's true. All right, so some people, when we were talking about where's that single point, that central point in the universe where that happened. Well, common misconceptions is that the Big Bang was a single point. It happened everywhere in the universe. And this requires you to kind of wrap your brain around the fact that the universe does not have a center from which it's expanding. Oh, the Hadron is the thing where they wanted to smash stuff together at a high speed, right? Yes, that's correct. All right, so we have to kind of wrap our brain around the fact that the universe does not have a center from which it's expanding, all right? The universe isn't expanding into anything, okay? Not like air into a balloon. So when you're blowing up a balloon, you know it's going to reach a limit and explode. Well, the universe is assumed to be infinite. There is no outward balloon that the universe is filling. It's just expanding. So, okay, so E equals mc squared. If you're confused on that, I actually have a video based exclusively on relativity on my YouTube channel. So, if you're on YouTube or if you're on Periscope, I have hashtag the science of relativity where I talk about the energy equation and all about relativity if you're confused on that. Okay, so, if we were to look at the current universe, yeah, like the surface of a balloon has no center, that's true. And the balloon would pop. But the universe, as far as we know right now, is infinite and continuously expanding. So if we were to take the universe as we know it and draw a grid, all right, with the spacing of a light year and attempt to put the Earth at the center, which we really can't, but if we're trying, then we put everything else in position to the Earth in this regard. Where do we draw the end lines? Where do we draw the end lines? We can't. At the origin of the universe, there was no spacing. There's the known grid. So if we go back to the origin of the universe and try to draw the grid then, it was ridiculously small and light years didn't exist at that time. So this is the conundrum of trying to draw such a grid. We make the assumption that the universe is infinite as things keep expanding and growing, but those lines, those drawn lines are changing. So, and there's no known opposing force to stop the universe from growing. So when scientists say that the Big Bang happened everywhere at once, what they mean is the universe didn't shrink to a point. It's literally that the spacing between two random celestial objects was essentially zero. Can I design the ICBM missile? You think the universe is infinite? We need to talk. I want to learn from you. Well, according to what we know and the understanding of how things are accelerating away from each other, and I'm going to talk about the evidence of that in just a little bit. So when we see the problem with trying to draw a grid based on the positions of things, when you go back to the early beginnings, the space between two celestial bodies was essentially zero. So it's kind of hard. Can I speak Persian? Unfortunately, I cannot speak Persian. So I'm going to show you an image that comes to us from NASA. All right. So this is kind of where we tried drawing this grid. All right. And we're looking at this. The very beginning, we have these quantum fluctuations. And from that, we have what we call the Big Bang, where essentially particles are moving away from each other. Then we have this afterglow light pattern. I'm going to address that here in just a bit. That afterglow light pattern is what we observe as cosmic radiation. We know it's there and we can see it. So that particular afterglow, because of what we understand in regards to quantum fluctuations, we have this afterglow light pattern. And then we move along that timeline. This is like a visual picture of my little boxes I had earlier of events. So as we move through, we can see less dense areas. So I'm going to take my little pointer here. So we got this lots of density of matter. But notice, matter gets less dense and spread out more. So we know that the universe is much older. Newer universe would have lots of stuff together, and then it would be expanding out. Isn't it much the same with how space still expands today, mostly in between galaxies? Nothing is holding the stuff in it back together, but it kind of just gets more like dough. You let it rest. True. So as we see, the universe is relatively expanding, so it's moving out into more space, but we don't have a limit for this. So notice there's the W map that we were talking about that's able to measure that cosmic radiation that we're seeing and able to determine the density based on the celestial bodies it measured. So this is something that we can measure and see. So a lot of people get this kind of confused. Why the shape of a glass? I think they just use that particular image. And keep in mind, when you're communicating concepts like this, I wouldn't say that that's to scale. It's mostly to try to help people understand, the density thing and the cosmic radiation thing. That's not exactly what it's supposed to look like. So when I use images like that, it's to help people understand, the expansion. And if we were to try to keep it in a box per se, we really can't. It'd have to be a stretchy box because we know the universe grows. So I wouldn't take that as the universe being a sphere. Does that make sense? But we can see this cosmic radiation even now. And that's a lot of what scientists base on it. So the universe isn't just expanding. The models, when they try to, when the term model, Dennis, I'm talking to Dennis, is, the term model is loosely used because models can change. They're just ideas to help us kind of wrap our brain around things, especially when people get into trying to understand that there's no central point. It happened everywhere and all at once. What's on the left side of the hug mass portion of your picture? I'm not certain what you were talking about there. So the universe isn't just expanding, but it's getting faster as it grows. So galaxies are moving away from us and they are accelerating. Some scientists believe there have been several inflations and deflations of the universe. So there's some scientists that think it's inflating and it's deflating. That may be dark matter having a role. Huge mass portion of your picture. I'm not certain what you were meaning there. It's okay if you have questions. I'm a kind lady. Well, thank you. All right, so, so the big crunch. So some scientists believe that there's inflations, like the expansion, and then there's deflations of the universe where it comes back together. And the thing is there is certainly a possibility of multiverses when you start looking at current inflation models. However, the jury is still out, as the evidence is not where it needs to be in order to accept multiple inflation and deflation events, as well as multiverse. But the inflation models would suggest that there are multiverses. And in addition to that, once we understand dark matter, we might, get more idea. Scaling is problematic if you go from nanometers or less to 90 billion. Yeah, that's true. You can't really take the image that I showed you that NASA gave us as scale. It's meant to educate, an idea of trying to help people visualize, So that's always a problem when you're a science communicator. And scientists, especially theoretical physicists that are able to take into their minds and work equations and kind of see, and that's why thought experiments are so important, especially when you start developing the mathematics behind things. Thought experiments are often used. And so that's where science starts, is with that. And then you develop the experiments, and then you go and you find the evidence for it. So that's kind of where we go. And, the E equals mc squared equation started as a thought experiment, and then he was able to develop experiments to show that gravity affects light through a solar eclipse. Okay, so now I'm going to talk a little bit about the evidence that we have in regards to the Big Bang Theory. Evidence! That's what scientists need. They always look for evidence, and they change their minds when they get new evidence. That's how science works. So how do they have this? The theories of particles. So the way that particles behave. Now, there are some things that they don't quite understand in regards to quantum when it comes to particles. But there are things, the ones that we observe, the ones that we can see. So theories of particles, the current theories of particles. Einstein's equations of relativity support the Big Bang. The expansion of the universe, we know it is expanding. That had to start from somewhere. And then also with the acceleration. Background radiation and also dark energy and matter play a role in this. So we know there's a substantial amount of dark matter. We don't understand it fully, but it's pulling us to bits. So how does that work? The science deniers hate when new information, thinking they were wrong before. But, that's the thing about being a scientist. You can't have a thin skin and be a scientist, because you have to be willing to accept that you're going to be wrong, and often. Most of science is failure, and people are like, science fails? Like, yes! Science fails all the time. So, you're like, because then you know what not to do and what doesn't work. And then you revise your experiment and find what does. So that's a lot of the times people who don't accept science think, well, they just think they're right all the time. Well, we've been wrong a lot. That's kind of what science is. Yes, and so there is convincing evidence for the Big Bang. That's true, and it's from several different sources. So I'm going to talk about this background radiation because that is more substantial. Now, we know that the expansion of the universe, that initial energy for it to get to move had to happen somewhere. And we know that dark matter is pulling stuff apart. We know that there's something called dark matter that has gravity, its own force, that's pulling stuff apart. Then we have Einstein's equations of relativity on how things move and behave in regards to gravity, how particles interact with each other. That's a thing. So quantum is exceedingly important in this, and there's still a lot of weirdness involved in quantum that they have to sort out. But so far, this is the working thing that kind of works. What do you think of Clementine taking pics of bases on the moon and NASA blotting them out? I'm pretty certain that's not a thing that's true, and I don't think there's bases on the moon. That's pretty expensive trips to go to the moon, and for nobodies who have ever reported bases on the moon before, seeing how you know, don't really kind of subscribe to that particular idea. But that's, you know, hey, what floats your boat, man? So let's see. You can't wait for James Webb Telescope. I have a telescope and I need to use it more often. So far the pieces fit, yes. But we, like science, we always need more answers. So I discussed the missions before that measured background radiation, but what was it? Okay, what was that background radiation I've been talking about so much? Physics tells us if we were to look at the universe, now I'm talking about physics in regards to astrophysics, quantum physics, various aspects of physics associated with particles, thermodynamics, as well as motion physics, all coupled together in astrophysics. That's what I mean by physics. Physics tells us if we were to look at the universe a millisecond after the Big Bang, we would see multi-billions of neutrons, protons, electrons, anti-electrons called positrons, photons, and neutrinos. So right after the Big Bang, you have this, what seems to be like an ocean of all of these different particles, just, you know, hanging out. Yes, people sometimes need absolute certainty, but that's the thing. We just don't have answers sometimes. So, like a second or a millisecond after the Big Bang, we would have an ocean of all of these quantum particles. So after a period of time, the universe, of course, it started out tiny, hot, and, you know, kind of like a really awesome relationship. You know, it starts out hot and awesome, and everybody's interacting. You're like, yeah, and then it just kind of cools down a bit. So, all right, so after a period of time, like a really awesome, like, you know, early passionate relationship, stuff cools down. Cool down. Then these neutrons, all right, these neutrons would either decay into protons and electrons or combine with protons to make deuterium. We can detect deuterium, all right? We can detect this, and the amount of deuterium in the universe is another measure of us to show that the Big Bang exists. That's an isotope of hydrogen, all right? Hydrogen is number 1 on the periodic table. It's the most simplest form, all right? So after that period of time, we would see these protons make deuterium. So once the universe cooled, it would reach an optimal temperature where electrons combined with nuclei to form these neutral atoms. These are atoms without charges. What elements were then? Well, I'm getting there. All right, so we started out, you remember I went through the little timeline. We started out with the smaller atoms. The smaller atoms being like hydrogen and deuterium. All right, so once the universe cooled and reached this optimal temperature, the electrons combined with nuclei to form neutral atoms, atoms without charges. So we got the larger atoms, then the larger atoms became molecules and compounds, but that was a long period of time. So before this happened, the universe would have been completely opaque, dark, kind of like melted licorice. All right, and the reason for this is because the non-bonded electrons, all right, these free electrons that weren't bonded to other atoms, would cause photons, now that's what we know as light, to scatter kind of like the way sunlight scatters from water and clouds. All right, so when those free non-bonded electrons were absorbed to form these neutral chargeless atoms and later become larger atoms, the bigger ones that we know, the universe became transparent. We could see through it then. These photons associated with this afterglow of the Big Bang, is the cosmic background radiation that we can detect with these missions, that can be observed with the instrumentation we have today. So that particular radiation is what we have in one of the forms of evidence for the Big Bang. That's exciting! Yes, somebody, Finno3000, is talking about hydrogen is 1 proton, deuterium is 2 protons, and then they go through. Everything else is the same. Hello, everyone. Hello. So that's kind of what we're talking about. And so I'm kind of summing it up now for you. If you just joined, fear not. You can watch this on Periscope later and also on YouTube. Melted black licorice, not the red stuff at the theater. Oh my goodness. So that kind of brings me to the last portion. Summing up everything, you know? The origin of the universe. I've talked about the expansion of the universe. I've talked about the origin of the universe. We cannot have things that are, the universe cannot be younger than the things that are in it, right? And we know the oldest thing that we can observe from the earth, looking out at the massive things, that's based on the rate that they're burning, their brightness. So we know that the oldest things we can observe on our earth looking out it's 11 billion years with certainty. 11 billion years old. The universe can't be younger than that. The universe is expanding and accelerating. It's about 13.8 billion years old now that we have information from 2012 and 2013 from the WMAP mission in NASA and the Planck spacecraft from the European Space Agency. And there's loads of evidence, but we always need more, especially with dark matter. Dark matter and dark energy is still a conundrum for many scientists. Who's my favorite Beatle? I do like my Beatles shirt. I'm not entirely certain. I kind of like them all together as a band. I did actually see Paul McCartney in concert once. He's the only Beatle I've actually seen in concert. And it was a stadium tour. And I got a free ticket. So I guess I'll have to say Paul McCartney because he's the only one I actually got to see in concert. So that's interesting. Since we asked me a question about the Beatles. So, if you missed this particular episode of The Science Of, you can check it out on my YouTube channel. This has been the science of the Big Bang Theory. Is the expansion slowing? No, it's accelerating. It's getting faster. Our universe is going to bits rapidly. So what happened before the Big Bang? I don't know, man. There are some scientists who think there have been several inflation, that's expansion, Big Bang, and deflation events. So it's possible there was a universe before us, maybe. Now, if you're curious about my sources, here are my sources here. I don't know if you can see these so well. So I'm going to just flip it over to this really quickly. The big monitor here. I'll put all of these on my website, scientistmel.com. I have several physics websites, space.com, nasa.gov. There's also a substantial amount of evidence associated, and you can go to nasa.gov and find out what their current missions are in regards to what they're doing to understand dark matter a bit more. Mel, I'd love to talk with you sometime about infinite versus finite universe sometime. Cool. No, I can't, but it should be after the time the microwave background formed, when it turned translucent as atmospheres comprised mostly of hydrogen are translucent or not. Huh. Lucy in the Sky with Diamonds. Quite appropriate for the Big Bang today. But, you know, if you guys ever have any questions, you can always find me on Twitter. I'm going to take a moment to thank my patrons because I have some new ones. Tony, Lauren, Jen, Carl, Melanie, Anthony, Paula, Daniel's a new patron, Carrie, Keith, Zachary, Tony, Graham, Tristan, and Jennifer. These are all patrons on my Patreon account. And if you can buy me a coffee sometime, my patrons start at $1 a month to get early access to my audio podcast. My audio podcast is Hey Scientist Mel. Hey Scientist Mel is a little bit different format than my show. What is my science background? I can run through that for a second. If you're curious about my science background, I have 2 bachelor's degrees in science, one in biochemistry, one in biology. I have a master's of arts in teaching, specialized in secondary science education. I can legally teach 3 subjects, including chemistry, biology, physical science, and I also have a master's of science in analytical chemistry. I'm currently an industry scientist, but I do this because this is important for me to kind of increase scientific literacy. So you can find me and my CV, all of the research that I've done. I've done cancer research in computational chemistry, as well as drug delivery systems and early detection systems. I've also done genetics research on the Tree of Life project. I made science interesting. Yay! I'm so glad. So if you want more stuff, you go to sciencistmel.com. All of my slides are there, in addition to quizzes, articles that I write, my audio podcast. After my patrons get access to it, patreon.com/sciencistmel. And I'm on Periscope, YouTube, and Facebook.com, and also an industrious YouTube content producer. Thank you. But, you know, if you feel like you like what I do, I also have a PayPal if you want to help me keep the lights on here, and this is great. And I have a good time doing this. So I'm glad I could be here with you. But if you're curious about my audio podcast, it's #HeyScientistMel. Use that hashtag and contact me on Twitter if you have any questions ever. But that has been the science of the Big Bang Theory, all of the evidence, the origin of the universe. It's amazing, and it's going to bits. Ah! And my websites are down there. You can test your knowledge on sciencistmel.com as well, and check out my CV and stuff I've done there. So thank you so much for watching, guys. I hope you've enjoyed this as much as I do. Check to my Twitter for the latest poll on the next Science of episode. This particular episode tied with gene editing. So I dare say I'll probably do gene editing next week, because it was a flat-out tie between Big Bang Theory and gene editing. So next week, I'm going to give it to the gene editors, but always check Twitter for new polls. Interact with me there. Talk to me there. You can also send me emails on my website. So thank you guys so much for joining. I'm so glad you're here. I'm so glad you enjoyed it. This was a lot of fun. So sending squishy science hugs made of, you know, quantum particles, because you can't really feel it, but it's there. Have a fantastic day. Bye.